Topic: Taylor's theorem and Maclaurin's theorem. Let's begin with Taylor's theorem. Let A be the fixed number and H is a variable, then f of A plus H is the function of H. Then the Taylor series expansion of f of A plus H is given by f of A plus H is equal to f of A plus H times f dash A plus H square upon 2 factorial f double dash at A plus H cube upon 3 factorial f triple dash at A, and so on. The nth term will be h raised to n upon n factorial nth derivative of f at A plus up to infinity. This is known as Taylor series. This is Taylor series expansion of function f of A plus H, where H is variable, about a fixed real number A. If we put A plus H is equal to X. So what I am doing is A plus H, this variable, is replaced by new variable X. From this, the value of H will be X minus A. So the above equation with this substitution becomes f of, this is X, is equal to f of A as it is, plus what is H? H is X minus A. X minus A into first derivative of f at A plus X minus A whole square upon 2 factorial f double dash at A, so on. The nth term will be X minus A raised to n upon n factorial nth derivative of f at A up to infinity. So this is also known as Taylor series expansion, but the difference is the above series is in the power of variable h. You can see that everywhere there is h, h square, h cube, h raised to n. So everywhere there is a power of h. So this is expansion of f in variable h, whereas this is the expansion of same function f in the power of x minus a whole square, x minus a raised to n. Now, so this is the Taylor series. Now if we put a is equal to 0, we get Maclaurin series. We get Maclaurin series. So remember that the Taylor series expansion about a is equal to 0 is the Maclaurin series. So let's put the value a is equal to 0 in above equation. So we have f of x is equal to f of 0 plus x f dash at 0 plus x square upon 2 factorial f double dash at 0 plus x cube upon 3 factorial f third derivative at 0 plus, and so on. So let's write its nth term. Nth term will be x raised to n factorial, its nth derivative at 0 plus up to infinity. So this is known as Maclaurin series. This is known as Maclaurin's series. So if we put a is equal to 0 in Taylor series, we always get Maclaurin series. Now let's write a few standard Maclaurin series. That is, I'm going to write the Maclaurin series of few standard functions. Standard expansions. First one is sin x. The series of sin x is x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial minus x to 7 upon 7 factorial, and so on. Second, cos x. It collects all the even power, so it begins with 1 minus x square upon 2 factorial plus x raised to 4 upon 4 factorial, x raised to 6 upon 6 factorial, and so on. Third one is tan x. X plus x cube upon 3 plus 2 times x raised to 5 upon 15 plus 17 x raised to 7 upon 315 plus up to infinity. Fourth one is e raised to x. 1 plus x square upon 2 factorial, x cube upon 3 factorial, x raised to 4 upon 4 factorial, and up to infinity. Fifth is sine hyperbolic x. It's similar to sine, but we do not need alternate sine and sine hyperbolic series. So this will be x plus x3 x raised to 3 upon 3 factorial plus x raised to 5 upon 5 factorial, x raised to 7 upon 7 factorial up to infinity. Cos hyperbolic x, it's similar to cos series but remove the negative signs. So 1 plus x square upon 2 factorial plus x raised to 4 upon 4 factorial, x raised to 6 upon 6 factorial up to infinity. Seventh is tan hyperbolic x, which is x minus x cube upon 3 plus 2 times x raised to 5 upon 15 minus 17 times x raised to 7 upon 315 up to log 1 plus x is x minus x square upon 2 plus x cube upon 3 is to 4 upon 4 x raised to 5 upon 5 up to infinity. Ninth, tan hyperbolic inverse x is given by x plus x cube upon 3 plus x raised to 5 upon 5 plus x raised to 7 upon 7 up to infinity. And the last one is 1 upon 1 minus x. So this is 1 plus x square plus x cube x cube plus x raised to 4 up to infinity. So last was 1 upon 1 minus x. This is its series is given by 1 plus x square plus x cube and so on. So these are the standard expansions, and all these are Maclaurin series. All these are Maclaurin series. That is, they are evaluated at a is equal to 0. Now let's take some examples on Taylor's theorem. So the first example is this. Using Taylor's theorem, express 2x cube plus 7x square plus x minus 6 in power of x minus 2. Solution. So let f of x is equal to 2x cube plus 7x square plus x minus 6. This function f is in power of x, and I want to convert this function into the power of x minus 2. So by Taylor's theorem, we have this: f of a plus h is equal to f of a plus h times f dash a plus h square upon 2 factorial f double dash a plus h cube 3 factorial f triple dash at a plus up to infinity. So what I will do is I will adjust this function. I can write f of x like this. I can adjust 2 with x minus 2 plus 2. It's one on the same thing. Moreover, I can write it as f of this 2 here plus x minus 2 is this. So if I match this with this, I get the value of a is equal to 2 and h is x minus 2. So here we have a is equal to 2 and h is equal to x minus 2. We can see that a is 2 and h is x minus 2, and this is in power of h cube, h square. So what I need to find is only f of a, f dash of a, f double dash of a, and f triple dash of a. So f of x, given that f of x is 2x cube plus 7x square plus x minus 6. I will find f of a, this thing. F of a, what is a? A is 2. So let me find f of 2. Instead of x, write a is equal to 2. Instead of x, put x is equal to 2. You will get 2 cube into 2, this is 8. 2 square, 4 into 7, this is 28. 2 and minus 6. So total will be 40. Now I will find f dash of x. Why f dash? Because I need f dash. F dash of x, this will be 6x square plus 14x plus 1, and then I will find f dash at a. A is 2, so f dash of 2. So this will be f dash of 2 will be 53. F double dash of x will be 12x plus 14. So f double dash of 2 is 38. F triple dash of x is 12. So there is no change in f triple dash. 2 is only 12. F fourth derivative is 0. So there is no need of finding any value beyond third derivative. So this formula stops here, because the higher derivative above this third derivative all will be 0. So let's put all these values in the above series. So therefore the above series becomes f of, what is a plus h? A plus h is a is 2 plus h is x minus 2. This is nothing but f of x, which is equal to f of a. Where is f of a? F of a is f of 2 plus h. What is h? H is x minus 2, and f dash 2 plus x minus 2 square upon 2 factorial f double dash at 2 plus x minus 2 cube upon 3 factorial f third derivative at 2. Stop. Let's put the values. So therefore we have f of x is equal to, what is f of 2? F of 2 is 40 plus x minus 2, f dash of 2 is 53 plus x minus 2 whole square upon 2 factorial is 2, f double dash is 38 plus x minus 2 cube upon 3 factorial f triple dash is 12. So let's simplify this and write the final answer. So therefore f of x is equal to 40 plus 53 times x minus 2 plus, this is 19, x minus 2 whole square plus, this is 6, this is 12, so this cancels with 2, so this is 2 times x minus 2 whole cube. So this is the expansion of the function f of x in power of x minus 2, x minus 2, x minus 2. Earlier it was given that this function f of x is power of x cube, x and x. Now we have expressed the same function in power of x minus 2, x minus 2